I just want to say hello and welcome to the next episode of Velo Virtual, enabling single stage to orbit the Aerospike revolution. When we started with this project, I didn't know what an Aerospike engine was. I started looking into it and just uncovering this amazing technology that I'm really excited to talk about today. So, if you think about space and the transition we're going through right now, we're looking at the access to space becoming more common. Everyone wants to get there to some degree. And for us as a species to get there, one of the barriers is cost and kind of lowering the cost. And we've seen a big shift to renewable or reusable systems. But even the most advanced rocket engines still feature multiple stages. So these discarded stages, these are the booster rockets that you see come off of the main system. They do get recovered, refurbished, and relaunched today, if you're familiar with the main company that does that. But what if there were a more elegant solution? What if we could do a single stage system for the entire voyage, and what would that do to space travel? And that's basically what the promise of Aerospike engines is in a nutshell. There's more to it than that, which our guests will talk about, but that's one of the big draws. And Aerospikes are really engineered to be as efficient at low altitude as they are high altitude. And that's a big difference between them and a typical engine. And that is what unlocks the ability to do a single stage rocket voyage. However, they tend to be very complex to design, to simulate, and then obviously to manufacture until now. And so today we will be exploring the design, simulation, and manufacturing of these Aerospike engine designs. It is an honor to introduce Ewan Craig. Craig is the founder, or Ewan is the founder, managing director, and chief engineer at Connect Everything Aerospace. He's a highly passionate individual who takes pride in creating innovative and boundary-pushing solutions like what you're going to see today in the spaceflight industry. He's currently studying and intends to take up running the company full-time as soon as possible. Also joining me is Kurt Chan. He's a senior product marketing manager at Ansys. He works with students, startups, larger companies to embrace and get the most out of new generation simulation-led product designs like Ansys Discovery. Prior to Ansys, Kurt spent several years as a mechanical engineer in the defense and medical industries. Aside from industry experience, he offers an expertise in a variety of 3D CAD and CAM tools, and complementing his knowledge in finite element analysis and additive and subtracting manufacturing techniques. Kurt holds a bachelor's degree in mechanical engineering from San Diego State University. So welcome, Kurt, to the show. Last but not least is Ben Wilson. Ben is a technical sales engineer at Velo3D, helping customers realize their innovations with Velo3D's support-free metal AM solution. Prior to joining Velo3D, Ben worked for 5 years in the metal AM group in both R&D and production at Honeywell Aerospace. Ben has a BS in mechanical engineering with a focus in jet and rocket propulsion from Embry-Riddle Aeronautical University. So plenty of rocket scientists on the webinar for you today. And with that said, I will turn it over to Ewan.
Thank you very much for that, Mike. So, yeah, I think I'd like to start just by talking about how you've come about listening to me talking about Aerospike rocket engines and how I've carried through that journey from the beginning. And it started for me way back in 2020, which feels like a long time ago now, and back when coronavirus sort of kicked off. And I was working at school at that time, and I started having a lot of time off school, sort of locked down, sent home. And I decided to start doing some interesting research, just finding more out about rocket science. It was something I'd always been really fascinated by, passionate about. And it was during that research that I discovered some really exciting things that I'd never heard of before. Just as Mike was saying, you find out these things when you start looking into it that you've never heard of before. And one of those was an Aerospike rocket engine. And the first and most shocking thing that I'm probably going to tell you is that these things were invented in the 1960s. They've existed for nigh on 50 years, and one is still yet to fly, effectively. A bipropellant Aerospike rocket engine has never left the ground. And as somebody who's always excited by the latest and most exciting modern technology, I couldn't understand why not. And that was what really pushed me to do more research into this technology. If these Aerospike rocket engines that deliver 100% of their thrust from the moment they leave the ground until they reach vacuum are so efficient and so much more advanced in the way that they can deliver power than a standard bell nozzle shaped engine, why aren't we seeing them everywhere? And why aren't the latest and greatest launch companies trying to develop this technology. So I decided that if nobody else was doing it, why not me? And I thought I'd give it a crack. So I started just messing around, designing really simple rocket engines in CAD, thinking, you know, how can I build towards building an Aerospike? And it just started snowballing, really. I did more and more design work, did some research that looked at some papers that MIT had released, talking about the equations they'd used to try and simulate these things. I decided I'd try and do it myself. I'd try and build an Aerospike rocket engine. And I can tell you that doing that from your bedroom is not easy. And you can see that the wall behind me is the wall on the screen. And that's what it looks like. So if you decide that you fancy doing a bit of homegrown garage rocket science, there you go. That's sort of what you end up with. It's constant design work, changing everything, always building on it. And you'll start with something you think is a great idea. You know, let's take this rocket engine, and its main problems come from things like cooling and manufacturing difficulties, and let's try and solve those. And then you realize that every time you try and solve a problem, it makes 10 new ones. And for me, one of those biggest problems, and we'll talk about those on the next slide, so it's the goals, it's about pushing towards those. How can we make these work? How can we bring something new to the table that's never existed before? If it can be done, it should be. That was the ethos that drove me to try and build this. And if we can make this Aerospike rocket engine work, if we can take something that was unfeasible because it was too expensive, too time consuming, impossible to actually keep cold, and turn it into something that's viable, you can completely shift the way that we see putting things into orbit around the Earth. If you can say to a newly formed launch company, hi there, would you like 10 rocket engines by next week? You can do that because you can just print 10 of them overnight. You can start that process and they can have several different design models to test, or a whole range of different cluster systems already built and prepared for them as quickly as they need them at a tenth of the cost of a traditional rocket engine. And that can be provided to any new launch company coming into the space. So that's really exciting. But of course, it's the challenges. So if we go to the next slide, it sounds amazing. It sounds like a holy grail. The Aerospike rocket engine, it's a romantic idea. It solves all the problems that we have in rocket science. Brilliant. We don't need to drop off stages into the ocean. We don't need to do a suicide burn and land something that's just come out of space onto a landing pad. We can just do it all in one go. But there is a reason this has not been done. And that's because the Aerospike is incredibly difficult to keep cool. In a traditional rocket engine, all of your exhaust gases are only touching one surface at a time, fundamentally, the outside wall of your combustion chamber, and they heat it enormously. And that means that you can cool that nozzle, the bell-shaped nozzle, really effectively. You can have regenerative cooling built into the walls of that chamber, keep it cooled really effectively. But if you look at the image in the background, and that's a slice through one of the meshes I made while I was doing some CFD, you can see that obviously an Aerospike has a bit in the middle as well, to put it in that sort of really obvious sense. And that's going to get much, much hotter than an external wall. So you have to keep that cool as well. And you're more than doubling the total surface area that's being exposed to hot combustion gases. So you can't use traditional cooling techniques and technologies to make this work. You have to come up with totally new ideas. And the real liberator for that design and that geometry was 3D printing. You can have channels buried inside of solid masses that are impossible to manufacture any other way. So I decided that I'd try and make this out of one piece and 3D print it in one go, because that takes out all that complexity that an Aerospike introduces to an engine and just turns it into a design problem, not a manufacturing one. Because if you think back to the space shuttle's main engines, there was actually an Aerospike variation design of those, and it had nearly 5 times as many components as the original bell-shaped nozzle. So it's foolish. It can't be done. Why would you use that when the other one works? It's just too expensive and too time consuming. So we have to try and solve those problems. And the real key to solving those was advanced support-free metal additive manufacture. So if we go to the next slide, I'm just going to let you take a quick look at this, because what you're seeing here is those cooling channels I was just discussing. So to make an engine out of one piece and keep it cool and have it be an Aerospike engine means that you need some of the most complex and almost absurd looking labyrinth-like two-pass cooling systems you can imagine. And you can try all you like to model how much fluid you need and how effectively it's going to keep the combustion chamber walls cool on paper. You can do the maths over and over again, but it just cannot be done without access to software like this. So in the background of this really fun image, you can see that I'm using Ansys Discovery. And that's a brilliant tool, because what it enables you to do is, in live real time, model the impact of a geometry change on a fluid simulation or a thermal heat transfer simulation and see how that will affect it. Try out changes, fiddle with your geometry. And for me, one of the big things was, well, just simply, how many channels do I need? I've got all these down channels flowing around the outside of the chamber. Do I need that many? Can I afford to cut down the number of channels and keep the pressure higher? Or do I have to increase the number and then perhaps increase my backflow pressure? And that's one of those really crucial aspects of using CFD. And it was Ansys that enabled me to do that. So I don't know if Kurt would like to say anything here, but I think maybe it'll be fun if you could talk a little bit about what makes Ansys Discovery so special.
No, thank you. And I think it's, and just a mic check. Can you hear me okay? Fantastic. So I think you nailed it, right? It's great to hear our customers talk about the success that they have with Ansys Discovery. But what's really key is you talk about like in real time or live. And I think a lot of us on this call who have used some form of simulation or CAD product, we understand it's all about time, right? And the beauty about Discovery is how fast can we explore, as you talked about the channels. You look at solving a problem like this would take in traditional simulation many, many hours to figure out. And within a couple of minutes, you're getting feedback just to understand what's going on, and then you can make quick design iterations. And that's what's super impressive about the technology that we're working on here at Ansys is leveraging, let's say, your GPU to split up to split up the computational time and speed it up. And then even you look at, as you mentioned, thermal, and if you guys are familiar with like terms like CHT or conjugate heat transfer, we all know those are hard problems to solve and figure out. So it's great when you hear your customers evangelize about the successes that they have and just how it's helped speed up the process of getting closer to solving the problem, right? And so at the end of the day, I've sit here and watched this video 10 times just because it's just intriguing to see, and we're looking at velocity, for example. Of course, we can switch the graph and look at temperature, but it's amazing what you can do with it, right? We've come such a long way with technology, and you're going to hear about it from 3D printing. I think it's evolved tremendously, but just even in regards to simulation, we all know simulation is hard to do, but we're getting one step closer to making it easy as possible. So we thank you for your support. Thank you for leveraging our products and using our trusted Ansys solvers. Back over to you, Ewan.
Thank you very much for that, Kurt. Yeah, and what I love about watching this little video here is just, you can see how complicated the internal channels are inside of this device. And that was the real barrier. It was trying to figure out how we can make an Aerospike engine that's going to stay cool and still be light and still actually have an optimized pressure adjusting nozzle. And it had never been done before. Nobody had ever made one of these things out of one piece. Nobody had ever, to my knowledge, even attempted it, because it was deemed, it's too complicated. How can you simulate that? How can you be sure it's going to work? And that's why you have to bring together and meld all of these different technologies, the latest in 3D printing, the latest in rapid simulation, and a lot of just fiddling in CAD. I believe that the model probably on the screen is something like the 500th prototype, and then the one that ended up getting printed was about the 1000th. So it's been a very, very long process. But as you go through that, every time you make a small change, you can quickly see if it's improved things, it's made them worse, and you can just work through that.
So I'm going to take a second to talk about Velo as a company to start off. We are relatively young. We started in 2014, but in October of this last year, we became a publicly traded company finally on the New York Stock Exchange under the ticker VLD. And what we've done really is we've created a revolutionary end-to-end metal additive solution that really allows designers to print these really complex geometries like the Aerospike without the restrictions of traditional metal additive. We focus a lot on high value complex parts. And we put a large emphasis on being able to produce these parts really repeatably without having the issues that you can have from going from printer to printer and from build to build. We provide quality documentation, things like that that reassure the customer that they're getting the same part every time. At this point, we have machines worldwide, but our software and our hardware is all produced in the US, and our headquarters are based in Silicon Valley in California. Next slide. So looking at the type of metal additive that we're talking about here, we work with laser powder bed fusion, which is probably the most common type of metal additive manufacturing because of the quality of the parts you can get from the process. The way it works is that you have a build plate that's riding on a piston, and first that piston drops down, and then a recoater comes through and distributes a thin layer of the metal powder. And then after that, you have a laser that scans and welds a cross section of the part. And then the piston moves down again. And this process repeats over and over until you've created a complete part that meets your intended geometry. Next slide. So in traditional metal additive, supports are a pretty common necessary evil that they're required to print some geometries at all that wouldn't be able to hold up otherwise. The reason being is that we are welding the material, so we are dumping a lot of heat into the metal. And if there's a substrate underneath, there's no issue with this. But in the case of like an overhang, there is no substrate underneath. So what happens is when the material cools and contracts, it tends to curl and warp upward. In a minor case, the result will be just a rough surface finish on that underhang or overhang. But then in the case of a more drastic overhang, the part material can curl upward and stick out of the powder bed. And when the recoater is coming by, it can crash into that and fail your build. Metal supports are made of the same material as your part, rather than like in plastics or something where you can have maybe soluble supports in some cases. For metals, these supports need to be forcibly removed with tools like pliers and chisels. So if you have supports in areas where you can't get these tools, that becomes a really constraining factor. So that's useful to note going forward. So the typical rule of thumb in metal additive is that you need to support surfaces that are below about 45 degrees. This isn't always the case. You can often push that level down to like 40 degrees or so, maybe a little more or less depending on the material and the geometry you're working with. But what I've shown here on the left is where the supports would be on one of the early models of the Aerospike if we were to support just to 40 degrees and below. You can see really quickly that some of these supports are in areas that you would not be able to access with these tools. So what it would result in is having to go back to someone like Ewan and have him modify the geometry of the part, which is really asking for a compromise for manufacturability. Sometimes that can affect performance or just undermine the intent of the part entirely. So what we've done is we have our system that allows you to print without these supports. On this particular part, the geometries that would require the supports on a traditional system would be features like these closures, these low angle channels that I believe are 10 or 15 degrees from the build plate. And then there's this local minimum that I'll talk about a little more on this next slide. So I've circled the local minimum up at the top left here. What this causes is what we refer to as a powder start. It's not the angle of the surfaces that's the problem here. It's the fact that it's building from a point that that is really unconstrained. So during the building process, when it gets to this feature, if it's unsupported, this would start out just floating unconstrained in the powder bed. And since we are dumping a lot of heat, your first problem that you approach is that you're putting a lot of heat into that small fragment, and that heat has no way to dissipate. So if you even do have a successful print with this powder start, you're going to end up with a really rough surface finish. What's more likely to happen is these fragments are very light. Sometimes they're light enough to get moved around during the recoating process, but more often than not, what happens is when this fragment finally merges with the part, the first place that it connects pulls that fragment in that direction, and this will curl up and warp above the powder bed and will fail your print. So what we've done is we modified the geometry to show what's on the right there to get rid of that local minimum. So towards the top of the Aerospike, in the build orientation, it becomes pretty conical in shape. And we refer to that type of cone shape as an inward growing cone. By that, what I mean is the diameter of the cone is decreasing as you move up in the build direction. The opposite of that would be an outward growing cone, like what's shown on the left here. And the challenge with an outward growing cone is that relative to the direction of the stresses that try to pull the part to curl inward and upward, this type of geometry doesn't resist that very well. So what you end up with is either a very rough surface finish if you're building a large cone at a low angle, or in a really extreme case, it can also protrude above the powder bed. In the case of the inward growing cone, it resists that stress very well, and we're able to build very large cones at very low angles oftentimes, which is why parts like this shrouded impeller shown on the right here are really some of our bread and butter parts, because we're able to print those shrouds really well without issues on our system. Another pain point in a lot of traditional additive is circular holes. Outside a pretty small size range, people have a lot of trouble with traditional additive with maintaining circularity or maintaining surface finish inside of circular passages. So we've really tried to expand the size range that we can do. A lot of times what you'll see on traditional additive is people will do like teardrop shapes to get around this. And in some cases that's fine. But in cases like where you need to optimize surface area for heat transfer, or not affect your flow characteristics by having some weird shape like a teardrop, we want to maintain circularity in those cases. And also another thing with the teardrops too is it also can lead to a stress concentration at the top of the teardrop. And in some cases, like in casting tooling, I've seen that cause cracking. At the very smallest, with a horizontal tube, we can print down to about 0.5 millimeter in diameter without losing circularity and fusing close. But we can also print above 100 millimeters in diameter and maintain the shape. And after that, it starts to get a little more dependent on what geometry you have nearby and things like that. If you tilt the axis of the tube just a little bit, even 2 degrees helps, that maximum diameter increases a lot. You can see on this compressor housing video, those tubes that are tilted at an angle. And what happens when you tilt it like that is, instead of the passage trying to close out all simultaneously with the horizontal tube, you end up getting what we refer to as a zipper effect, where the roof of the channel closes gradually and reduces the stress during the print. So just looking at what was done specifically on this Aerospike, you'll first notice that there's a filament attached to the bottom of the part where it connects to the build plate. This is more of a precautionary measure. We add this on all of our parts just to reduce the likelihood that there could be any cracking at the interface of the build plate. We also added these powder evacuation perforations, and those are to allow powder to fall out of the part after the print. If you don't have these, then you can either really upset your EDM operator because the powder will fall out when they go to cut it. You could also end up having powder stuck inside the part, and that can get solidified during the heat treatment process accidentally, and then your channels aren't useful inside the part. But so that's why those are important. We also made some very slight CAD modifications with Ewan's help, and what was changed was we increased some thickness where some of the channels merged, and then we also added some fillets in those areas just to smooth things out. We also eliminated that powder start that was mentioned earlier, but other than that, this part didn't require any support on our system. So we just put them on the build plate in flow, and they were ready to go printing. We just did 2 on the build plate in this case, but we could have easily fit more if we needed to. So something that makes the support-free printing possible is the fact that our preprint software Flow is able to automatically identify the geometries in the part and apply really custom specialized scans in terms of power and the vectoring that's applied. For instance, like the closeouts and the low angles on this part, Flow automatically will apply really delicate scans with really tailored vectors to maximize the surface finish and maintain the dimensional compliance of those features. In areas like the bulk section of the part, it'll run the laser at its maximum power output of a kilowatt, and it'll really run through those areas pretty quickly to maximize throughput. But then in like areas where there's a vertical thin wall or something, it'll work to manage the heat a little bit better to prevent overheating and to maintain dimensional compliance. I mentioned earlier that we actually offer a full end-to-end metal solution. It's not just a printer, it's not just a software package. We go everywhere from the beginning with preprint in our software Flow, where you set up your build layout. From Flow, you generate a Velo print file, which can be transferred to any of our Sapphire printers across the fleet, as long as it's the same material and machine model. During the print process, we have Assure, which monitors the process, but also can put out quality assurance documents that you can provide to the end customer. And we'll talk about that a little more on a later slide. So looking at the Sapphire print family first, in the case of this Aerospike, we printed this on a standard Sapphire, which is a 315 millimeter diameter circular build plate with a maximum height of 400 millimeters. On board, there's 2 1 kilowatt lasers that are run to their max capacity, and they can also scan the entire plate individually. Then we have the Sapphire 1MZ, which is basically the same as the standard Sapphire, except the height has been extended to a full meter for really tall parts. And then our newest printer is the Sapphire XC, which is a really large 600 millimeter circular build plate with a 550 millimeter Z travel. It's also got 8 1 kilowatt lasers to maximize throughput. I'll show a list of the materials a little bit later on, but all of our materials are printed at a standard 50 micron layer thickness in an argon purged environment. We have over 900 sensors on board that are monitoring the print process, and in some cases, such as laser alignment, are making live corrections to make sure everything's running properly. Something that's really unique about our printers that make support-free printing possible is our non-contact recoater. So in traditional metal additive, you typically have a recoater that has some sort of a blade or a brush that pushes the powder across the build plate. And if you have really delicate geometries where you don't want to disturb those geometries during the build, what can happen with a standard blade is it's really whacking the part every time it goes by, and that can really make or break your print. So with a metal blade, it can really just kill the print entirely. But maybe with a polymer blade or a brush blade, it might conform and erode away instead and allow you to have a successful print, but then you're left with the question of whether that material from the blade is actually embedded in your part. So what we have is a recoater that maintains a healthy gap above the part, never actually contacts it. So the way it works is the recoater moves to the front of the machine, and then on its way back, you can see there's a dispenser that is starting to distribute powder at a very thick layer thickness that's much taller than the actual layer thickness. And behind that dispenser is a normalizing blade that is also very high above the bed. And all it is doing is just smoothing out the layer that's been laid down. And then behind the normalizing blade, we have a proprietary powder removal process that comes and removes the excess powder and gets the powder bed to the actual layer height without ever touching the part. And so once it has done it all the way across the entire bed, you are ready to get back to lasing, and it starts the process over again. In the event that you do have a protrusion on our system, we have a height mapper on board that is able to detect those. Every layer, the height mapper is looking, it takes standard camera images as well as structured light images to map out the height of the powder bed. If there is a protrusion that is high enough to be concerning, it will flag it in Assure so the user can see that it's happening and they can pay attention to it. If it gets high enough to where it's at risk of actually contacting our recoder, it'll pause the build to prevent any damage to the machine or to the part. It's really nice to have this as a troubleshooting tool if you're looking at it in real time, but also after the build if you need to understand what might have been going on during your print and if you need to make any decisions on things to change going forward. So Assure is really, it's our monitoring and our reporting software that is really important to the Velo system. For me, I have parts printing at our headquarters in California daily. So it's really nice. I can log in from here in Arizona on a VPN and log into Assure, and any of our printers that are on our network, I can look at the latest height mapper images all the way up to the current layer. I can look at all the important sensor values, make sure they're in healthy levels during the print. And then when the print is done, all that data is stored as well as these sensor data plots, any interrupt summaries, any error messages that could have popped up. All of that is stored and can be downloaded as a PDF as well and can be provided to the end customer. It really, since our print files can be run on any Sapphire across the fleet, it's really useful for a customer that is printing at multiple locations. They get a warm and fuzzy really from this document that is reassuring that the print file was executed the same way every time, because there's all these calibrations that are kept track in this build report, and then all of the sensor data to make sure the machine was behaving as expected. It's a really useful document to have. So looking really quickly at the materials we have to offer, our material selection does expand based on industry demand. Since a lot of our applications have been aerospace and some more extreme environment applications, you see a lot of these nickel alloys to the top here. These are our qualified materials. We also have Ti-64, and there's F357 aluminum, and then Scalmalloy, which is another aluminum alloy. Coming soon, we have GR Cop 42, and then we have stainless 415. And lastly, there's 6061 aluminum, which has been a material that we've all wanted for a very long time. The powder suppliers are finally getting to the point where they have 6061 that's usable, and we're in the middle of qualifying it on our systems now. Our systems are intended to be powder supplier agnostic, so you don't have to stick with powder vendors that we've worked with if you don't want to. As long as your powder meets the spec, it should run in our system. But with that being said, we do qualify our machines with partner vendors. So if you do want to stick with the vendors that we work with, we can also help you source that powder so that you're running the same thing we run internally as well. So here's a video of the actual build from the images in Assure. You can see at the beginning there was the powder channels, or the low angle channels shot out really quickly out to the side, and then we got into those thin walls with the channels. And at the top, you see that conical inward growth that comes to a closure, and then you end up with what's a beautiful part. Mike did a really good job at compiling this video. It's kind of mesmerizing to watch, in my opinion. But this turned out really well. So this is what the part looked like from the outside and on the inside after it was cut off the plate and sectioned for viewing.
So if we go to the next slide, and this is where it gets exciting, because if we can take these single piece rocket engines, we can manufacture them at speed, we can verify how well they're going to work, and we can actually manufacture them for 1/10 of the cost of something traditional that's existed for a long time. You open up a whole new world for small, low-end investment into the space industry. Because if you think about it, we can say that what's happening with reusability is really exciting, it's fabulous, but doesn't make it any cheaper to start. Yeah, it's great, you can now use the same engine over and over again, but it still costs $5 billion to build the thing, so it's not really that amazing if you're a brand new launch company trying to put some nanosats into low Earth orbit. We need that low cost to entry. We need to remove that high barrier. And that's what 3D printing and Aerospikes allow. A single cluster of Aerospike rocket engines, which are going to deliver all the thrust you need from the very start of your flight trajectory to the end, open up that possibility. Because with a traditional DeLaval or bell nozzle shaped engine, you can lose up to 50% of your thrust during the flight trajectory. And that means you have to have either twice as much fuel or twice as many engines. Both of those cost you a lot of money and a lot of mass. And with putting things in orbit, every kilogram is thousands of pounds. So every gram you can save is crucial.
All right, thanks, Ben. Thanks, Kurt and Ewan. So we do have a couple questions coming in. I'm going to go ahead and stop sharing so we can all kind of be on camera here, get a little FaceTime. One of the questions that we always get is, will there be a recording? And so in case you missed it at the beginning, we do provide a recording to this presentation. It'll be in an email between 24 hours and 48 hours. So by the end of the week, you'll get an email with a direct link to the recording. Also, if you want to reference this and you, for some reason, missed that email, if you go to our YouTube channel under the Vela Virtual playlist, that's where our entire library, it's about 24 different videos, and they're all similar to this. So I do want to kind of get into one of the questions here, and I think you, and this is maybe more for you. What method did you use to design the contour of the spike body? That was Noel wanted to know that.
Yeah, okay. So for me, designing the actual contour geometry of the Aerospike inside the engine came down to a couple of different methods that I ended up using. So I started by finding a series of equations that a gentleman who was doing a PhD thesis on Aerospike rocket engines over at Caltech, I took a look at some of the papers that he produced, and he'd found some equations that he'd put together, which he thought mapped pretty accurately a fairly efficient Aerospike slope path. And I used some of those. And then I also found a series of equations that some NASA guys had done. And I put those together and I designed a few basic contour shapes. And I simulated those, and I wasn't very happy with what I was seeing. So basically what I ended up doing was actually designed a piece of software that took a couple of equations that I found, integrated them into a through and through piece of software. So I'd input a couple of parameters and it would spit out a contour for me. And then I'd simulate that and see the kind of results I was getting off of that simulation. And what I ended up doing was graphically modeling on like a line graph how effectively each of these Aerospikes was working. And I used that to decide on the final contour of the spike. And then it just comes down to how much truncation you want. Because obviously one of the really fun, kind of not fun, interesting things about an Aerospike is a truly efficient one is infinitely long. It's obviously impossible. So you have to decide what percentage or what degree of truncation you want to do. And for me, that came down to weight saving and also the theoretical ability to keep a thing cold. You need to be able to pass liquid through it. So it has to be a certain diameter, certain thickness for structural reasons as well. So I ended up, truncation came down to a materialistic view. But yeah, so it was a couple of aspects that I brought together, I wasn't really happy with. So designed a little piece of software that just did some equations in, graphically modeled the results so I could find which one was looking the best.
And kind of a follow-on to that is, what are your plans for functional testing? Has this part been tested yet? And
so this is absolutely the next thing. And so part was printed, I reckon, what would it be, 3 or 4, maybe 3 months ago now. And from the very beginning, the plan was absolutely a static test fire on the ground. And that would begin with low pressure, short runs, probably running very, very oxidizer rich to keep the temperature flow down and keep that fuel and flows really high so I can make sure I'm keeping it cold, and then just work up closer and closer to some sort of operating pressure, seeing the kind of responses we get on the thrust output and also on the cooling, because that's the big thing. My fluid and CFD stuff seems to think the cooling works, but obviously, as we all know, got to get it out in the real world. So a static test fire, and the plan for that has always been within 2022, trying to get a static test fire going, and the time frame has been being pushed away, but that's definitely what's coming next.
Absolutely. Ben, I'll flip this one to you. This is actually one of my favorite questions. Can you print parts that are rotational in nature? Obviously this one's a static component, but can you talk about our experience with rotational components?
Yeah, I've actually printed quite a few rotating components, especially in oil and gas. A lot of pump components, impellers, things like that. That's a very common application for us. So yeah, we do.
And any numbers on any of the performance on those or testing conditions of those?
I don't have anything specifically off the top of my head. I don't know if you have anything like that, but yeah, I don't think I have any actual hard data on that.
Yep. We did have one. We did one of these webinars a little while ago with Ansys. Actually, it involved Launcher, and so Launcher's a rocket company out of the U.S., out of Southern California, and one of our printed impellers was 30,000 RPMs cryogenic conditions. So you're looking at tens of thousands of RPMs for these. And I know we've got you showed the Hanwha one as well, which I believe is tens of thousands. I don't know what the exact number is, but that's a supercritical CO2 application, which now you're talking about extremely high temperatures and very wide pressure ranges. So pretty cool stuff. So we do have another one, and you referenced this earlier in your presentation. So Ben, this is probably back to you again. Can islands or local minima be printed in the Velo Sapphire? And how would you approach printing them if you had them in as a design? What are some of the options that you would use?
Yeah, you can put some pin supports or something at the very tip, just so it's a very minimal obstruction at the bottom of it, but it's really recommended against printing those. It's very rare that you have a successful case when you're printing a local minimum like that. Yeah, it's typically what I was explaining earlier, where it might be stationary until it attaches to the part, and then it gets tugged just by the internal stresses of the print process, and that local minimum, that little fragment, ends up moving pretty easily. Okay.
And one of the thoughts I had is, I know you and we kind of worked with you on getting this part, but if Ewan were to scale into production, would he need to buy a printer, or what would be the process to get more of these manufactured?
Yeah, so we have a contract manufacturing network that Velo works with, and you can reach out to any of those manufacturers, and or reach out to Velo directly, and we can help farm it out and make it send the parts to the correct manufacturer that makes the most sense based on what materials they have, what machines they have for size constraints, things like that. And yeah, and we help bridge that gap.
I think that's something that I've actually thought about as well. And I just want to say that obviously in the long run, it could definitely become effective for connectivity in the aerospace to own its own printer, or even in a more interesting sense for upcoming launch companies who want to build their componentry to own their printers, and then they just come to CEA and look to us for design solutions, so we can give them the engines that they require, the specifications they require, and then they can go ahead and print them as much as they need. So that's another option.
There you go. So you got a design resource here in CEA and UN. We've also got a printer. It just started printing, I think, this week, its first production parts, and that's SBOT, and that one is locally available in Europe, and they're printing in 718. So you kind of have this whole system if you want, even in right there in Europe, across the pond, as they say. So there's a question here about planar Aerospike designs, and I'm actually curious, have you looked at those, and what would be the differences between that and what you ended up with in terms of the design?
Yeah, so obviously I've got a toroidal Aerospike, and my main choice, and the reason that I decided to go and test a toroidal Aerospike, and why I think it's the best choice, is because I think one of the biggest issues for Aerospikes is that people try and make them not more complicated, but people think that they can't just design them as an Aerospike from the ground up. They have to be based off of something that already exists. And I think that keeping the whole process as simple as possible is definitely the best idea. And if we want to keep down that barrier to entry, that cost and that manufacturing time, then a toroidal Aerospike is rotationally symmetrical. It's got, I think, more inherent strength, and it can be printed in one piece, whereas a linear Aerospike, especially if you've got sort of maybe opposed planar, that's going to be much more difficult to print, and also scaling is much more difficult, and then containment of exhaust gases becomes a more complex process, because you're going to need to have a combustion chamber that's separate from the Aerospike, whereas obviously in the design that I've gone with, the combustion chamber is actually held together and surrounded by the Aerospike itself, so you can control things like vibrations, because you've got a circular shape which has got that really good structural integrity. And also it can be based off of those basic equations that describe the volume you need for a combustion chamber. And you can use those to figure out exactly how large you need to make your Aerospike. So you can just keep the whole process a bit simpler and stop making Aerospikes quite so complex and start making them more feasible. So that was kind of my thinking and why I went to Roydal.
Very cool. And if you are interested in a linear one, I'm sure Ben would love to try and print that one too. Always happy to try those out. Yeah,
sure they could.
So Ben, you mentioned Flow and kind of this preprint software, and then just kind of answering this question here. Is that a separate software company, or is there additional charge to that?
No, with the Sapphire printer, yeah, Flow comes along with that as well as Assure. It's all part of the package that we call this end-to-end system. Yeah. So.
And do those work with other printers as well? Is that something you can just kind of attach on?
No, Flow is meant to directly work with our Sapphire printers. It has all of the special processes and stuff built into it in the background. So it's specifically meant for working with setting up the build to work with how our printer operates.
Very cool. I mean, that's the questions I've got. If you want to get your question in, I'll give you a couple more seconds here while we kind of say our closing remarks. But Ewan, let me turn it over to you to do some closing remarks here. What are your kind of thoughts on this whole process? How did this work out for you? And then what do things look like going forward into 22?
Yeah, definitely. So I think what fundamentally all of this fabulous technology comes down to is liberation. It's reducing compromise. And for me, Velo 3D, if the people in this chat are interested, Velo 3D was not the first company that I was looking at to try and manufacture this product. And the first companies I looked at, they didn't even say no, they just said we can't. They said it wasn't possible. And to avoid sounding like a salesman, these guys did it. Nobody else could. And for me, it was either completely go back to the drawing board and get rid of this brilliant new exciting idea that I come up with and just turn it into something that already existed, or work with the people who can really push the boundaries and make it happen. And that's what's exciting, and that's what's going to really change the way that I think the entire space industry is both funded and also researched and developed. Because I think for so long it was either so expensive and so enormously complex that it was states that could do it, NASA and the like, and ESA, that was the only people who could get involved. And then some incredibly wealthy people decided they wanted to have a go at it, billionaires and the like, and they've been quite successful. But I think, as with almost any industry, the sign that it's becoming more and more important globally is when smaller companies are able to start getting involved, and private investors, genuine sort of startups, and that's when it becomes exciting. And it's companies like Velo 3D and Ansys who are actually enabling all of that to start having a big resurgency. And I think in the UK especially, I don't know how many of you guys on the call are from the UK or get involved in business there, but we've been pretty dormant in the space industry for a fairly long time. I think we'd all happily admit that. And it's this sort of tech that's going to change that and bring us back into the playing field, and also enable other smaller countries that don't have enormous state-funded processes to also get involved. And it starts with things like simple rocket engines that can be built quickly and cheaply and are really efficient, and it just grows from there. And that's what it's exciting. Nice,
powerful words. Kurt, I'll turn it over to you.
No, it's brings a tear to my eye, right, to hear this kind of stuff, right. And it's from the heart and genuine, right? And so just to back up with the great words around Velo, it's great to see the partnerships between two mega companies, right, help out startups or the community. I think that's what it comes down to. Is you look at, like, people might hear this and be like, it's unattainable and unreachable for me having this idea or invention, but it's possible, right? Like, yeah. We're here to help. We're here to help the next innovators, and specifically at Ansys, right? We all know the price of software is expensive, but we have programs. We have the startup program, we have the entrepreneur program, we have the academic program. So whether you are in academia or you're a startup and you don't know how to get a hold of software, we all are here to help, right? And I think that's that's why we do this. This is why we come to work. We love working with companies like C-Space. We love working with our partners like Velo, and it's been a great relationship. So for the hundreds of people that are on this call, right, keep that in mind, is we're here to help and we're here to inspire. So we appreciate this partnership at the end of the day.
Yeah, and I'd say just, you know, if you are a member of the Ansys Startup Partnership, that is a great resource, because I mean, you can design it, they can simulate it, and then if it's the right application for us, you know, Kurt and I talk all the time about getting the next application printed, and we'll get you from an idea to real hard metal in your hands, and that's a massive step, right? And you know, that's not something that's available to everyone all the time. So I would say great partnership, and there's a conduit into getting real world metal printed and getting the stuff available to test. So, but Ben, I don't want to leave you out. I'll leave final words for you.
No, I just want to say, yeah, it's been great working with these guys at Ansys and with CEA Space. You know, this has been a fun project, and you know, there's obviously it's going to be ongoing for a while. There's a lot to do to get to space, and yeah, and I continue to enjoy it. So.
All right. Well, thank you, everyone, and happy belated Valentine's Day. I hope you loved this presentation about Aerospike engines. Great job, everyone, and thank you, audience, for joining us today.
Awesome. Thank you again.
Thanks a lot, guys. Cheers.